Okay, so when the time reaches to about 2 p.m. the pump should turn off, and then when the time reaches up to 17 hours or 5 p.m. the pump should on. So I will add another condition, add a simple new condition, clock time. There are also different. Oh, ध्यान दीजिए. There's also some different options. Based on that, you can also control the closure of pipe or the valve, and for the pump as well. And so based on that, you can use these different options as well. So when the time reaches up to 5 p.m. the pump should turn on, adding another condition. So the pump should turn off at the 21 hours, about 9 p.m. So now the pump should turn off at the 9 p.m. because at that time the demand decreases. Turn off. So from here you can observe that the pump will turn on. First of all, I have made the status of pump at the start of simulation to off. It will off at the start of simulation, and 4 a.m. it will on, and then 8 a.m. it will off, and at 11 a.m. it will again on. At the 2 p.m. it will off due to decreasing in demand. Similarly, at the 5 p.m. it will again on, and at 9 p.m. the turn will be turned off. So this is basically for this type of criteria is basically most used for the intermittent system, and mostly in Pakistan the intermittent system are designed. So now I will run the model. So now you can observe that the demands, or you can also observe from the summary that the start of a simulation, the pump turn off, so the water is not supplying to the system, and at the 4 a.m. the pumps turn on and providing a water up to 7 a.m. and at the 8 a.m. again the turns become turn off, and then started at the 11 a.m. So in such a way you can design an intermittent water supply system. So in spite of that, I also want to show you that, for example, if I want to add a tank to the, you can observe here the values. So these values are basically very high. You can also provide a pressure reducing valves and isolation valves, different valves in the system, in order to control the supply of water through this pipe. And I have also show you the criticality. So by using that criticality analysis, you can observe and find that which portion of a system is critical, and based on that you can provide a walls to a system in order to prevent the system from criticality. So now the other options I want to show you that, for example, in this time, basically in this time when the pump turn off, I want to supply a water through tank. So what I will do, I will provide a tank here, and in a water supply network, designing a tank is a very difficult task. I will make a die of this rising man. Basically, this is a rising man providing water to the the tank, and then when the pump turn off, it start draining in order to fulfill the demand. So I will just show you the one pump, one tank, and though I think for this system, the one tank will be not sufficient in order to fulfill the demand, and similarly, and it is not appropriate to use such a high pump for that system. So you should use 2 or 3 pumps if available of a high of a low discharge and having low discharge but giving a high head of water. So that is very appropriate for a system. So by using 2 or 3 tube wells, so it will be good for a network to fulfill the demand. So I am keeping just 300 millimeter about to very about 600 1 feet dia of a pipe. Okay, so I will define a perimeters of a tank. So first of all, base elevation. I want to calculate the base elevation of this tank. So I will make a selection tank, then go to the tool, click on the T-Rex, towards, select the file, and select a meter elevation, selection set, tank. So basically the elevation to that tank is designed. Select this tank. Here's the elevation. Why it's not showing? It should be updated. So the elevation. So here you can observe that the elevation to the tank has been designed. So I want to change the unit to meter. I want to design 15 meter of tank. So the elevation from a ground, the base elevation of a tank from the ground is about 15 meter, and I want to keep it for that purpose. I will make a level. So it 15 meter above the ground level, then 16 meter. If the minimum level of water in a tank should be of 16 meter above the ground level, and the initial should be of 17 meter, and the maximum level should be of 22 meter will be appropriate, and the diameter of a pump should be of 5 meters will be sufficient. It is circular. So at the start of simulation, it will not pull, therefore what I have to do. Okay, let me run the model.
सर 1150 मीटर से ज्यादा एलिवेशन है
دا خو جی دغه دی کنه جی 1150 میټر خو دا غزه حساب سره دی جی ډیټ هم دا خو د ډیټ هم نه دی
डेटा मींस कम लेना सर
ډیټ هم اوس چې کم یو ټی ایم دی کنه د یو ټی ایم خپل ډیټ هم دی نو 1150 میټر دا د ګراوند الیویشن دی سروے کې تاسو اس بیسیکلی
ټیک شو جی
پوه شئ
ګراوند الیویشن
ګراوند الیویشن دی
ها جی ګراوند لیول
Basically, at the start of you can observe that at the start the pump is off. Therefore, the values here are showing in the negative because the water is not supplying to the system. It is an intermittent system, and we are trying to design such a system that at the time where the pump is shut off, the demand should be fulfilled by the tank. Okay, I want to check graph. You have to keep changing these values. So this is the way in order to design the tank that you have to select by trial and error method. But the pump, I want to open a pump at the start of a simulation. Let me open a pump. The first simulation it should run. So basically the tank is not sufficient to fulfill the demand. Basically the demand is very high, therefore 4 to 6 tanks should be required in order to fulfill that demand. So basically this is a one-way tank. When the pump is started, then the demand is only fulfilling from the pump, and it also providing water to the tank to fill the tank. And when the pump turns off, the tank providing water uh, to the system. So this is the way in order to model the tank, and then you should play around with these values by increasing the size of a pump, by increasing the head of a pump in such a way that it should fulfill the demand when the pump turns off. And always try to let me select both of these. Okay, so basically this is the flow of a let me the flow providing by a pump. So at the start of a simulation it drops because it's all water is providing it to the tank. So it should be designed in such a way that it should fulfill the requirement of a tank as well as the system as well. So you can observe from here. So now after 3-4 p.m. the tank start draining, and then again what is provided to the tank uh, I also want to show you the system head curve. Basically, the pump is not sufficient in order to fulfill the demand. Therefore, it is not going a proper value. Therefore, the pump should be in such a way that the head curve should form like this in order to fulfill the demand. So designing the optimizing the pipes and optimizing a tank will take too much time. So I will stop here, and you should try to change these values and also try to add more pumps in such a way in these uh, areas where bare lands or in areas where no such plots are available. You can provide it the tank or tubewell at here and also provide it here. Similarly, you can also provide it here. So by using these lands, you can provide tanks and also a pumps or tubewell in order to fulfill the demand economically. So I also want to show you the for example, you want to find the energy cost of a pump, then you can do it. And just let me. I want to. First of all, you will create a tariff. I took these values from Pisco website. The rate of electricity, the rate per unit per kilowatt hour, and per kilo the kilowatt hour is basically equal to 1 unit. So these are the block rate I just put in here, and I define energy pricing as I define here by block rating. Just put in here. I also select a pump for the system. And then run the simulation. It gives me the total energy utilized by the pump. Similarly, the how much volume provided to the system by a pump, it is about 2.9 million liter, and unit energy used per million liter. Similarly, how much the durations the pumps run. It's also provide me the different value that at different time of interval, the flow providing by the pump. Similarly, the pump head, the volume provided, and the water power and pump efficiency at different time interval you can observe here. Basically, we are using the intermittent system, so in some places it's showing a zero value because of not running the pump. Similarly, you can also observe the. So that's all about the energy calculation, the energy cost calculation. And you can also do energy management in order to find, for example, if there's always inflations occur in our electricity system, the price in the price of electricity. So you can also use the value of interest rate of 4%, means that there will be 4% of inflation up to 20 years, and you want to check a billing period for 30 days by providing a meter as well, adding a power meter, and then providing the energy pricing as I defined earlier, and you can calculate the energy cost. So you can observe for the 30 days, the total energy uses amount of this value, and the total billing period for the 30 days is about 66,832 kilowatt hour energy use. And you can also observe the So this is basically giving you the total energy cost in 30 days. So this pump is basically very uneconomical, but here I just want to show you that for the water supply network, the pump should be optimized. You have to select different number of pumps. uh, Similarly, there's a lot of curves here you can use and select here of pump in, of such value. For example, if you want to fulfill the demand of 800 gallon per minute, then you can use a two pump of 400 gallon per minute to fulfill the demand of a water supply network. And so based on that, you can minimize the electricity utilized by these pumps, and based on that you can also use a pump or a tank at the time interval where the pump is shut off. You can minimize the electricity cost as well by turning off the pump and fulfilling the demand using a tank. So that's it about the pump selection and how to design a pump for a continuous water supply system and for the intermittent, and similarly for the intermittent system with providing a tank in order to fulfill the demand. And the other step, I want to show you that how to report finalize your report of your water supply network. So the WaterGEM is very flexible, and you don't need to use a AutoCAD in order to make a report for a water supply network. So I will start another session for this. So I am going to end this session.